I think we're good to go.
Hello, everyone. Thank you for being here on the Lute Along today for this technical talk about guitar acoustics. I'm your host, Giuliano Nicoletti, and today with me, there is my friend and colleague, Martino Quintavalla from Italy. Hi, Martino.
Hi.
So Martino is a great builder of mandolins, but he also has a PhD in materials engineering. And over the year, he's teamed up with some top luthiers. He has done some cool research on wood and mandolins. And he's teaching acoustics in a luthier school in Italy, la Civica Scuola di Luteria di Milano. So we first connected when I was working on my book, Mastering the Sound of the Acoustic Guitar, that you might know. So I was intrigued by his research, and he was kind enough to share some of his publications with me. So eventually he ended up being a huge help in getting the book finished. And about a year ago, we were collaborating in some research project, and we realized that a comprehensive work about soundboard design method was missing. A research to compare different approaches and evaluate the pros and cons of each one with a methodical analysis. And also, very, very important, some useful conclusion to provide clarity for guitar builders. So one thing led to another, and we decided to launch the research project together, which culminated in the publication last month in the Journal of Acoustical Society of America of a paper, Survey and Evaluation of Classical Guitar Soundboard Design Methods with Finite Element Analysis. So today we are presenting this project for the first time to the community here on the Lute Along. And since this will be a bit more technical than usual, than the Back to Basics series, we are asking you today to use the chat to pose questions during the presentation. But Ian, you can hold the questions. Max, also, if you want to help us to coordinate with interventions. But we hold the questions until the end, because this will allow us to provide a comprehensive overview of the research in about, I guess, half an hour. And then it will be followed by an interactive discussion. So,
sounds good. Just to reiterate, everybody, hold your questions to the end today.
But write the question on the chat so we don't lose the questions. And then we will go back to trace everything. Okay? So we will present the research together, and I will begin. The sound of the instrument of an acoustic guitar is radiated by modes of vibrations of the soundboard, and the first 6 resonance modes of the acoustic guitar are usually responsible for around 85% of the sound emission of the instrument. And the amplitude, the intensity, the frequency, placement, and the distribution over the whole frequency response of the guitar are largely responsible for the timbre of the instrument, for its sound, its tonal balance, and also for intonation of the guitar. So the problem is that tone wood parameters are not consistent. Here you can see measurement of several samples of Italian spruce and Swiss spruce. This data comes from a research from Martino and Simone Bononomi of Wood and Tones. And we can see that there is a high dispersion of the parameters of tone wood. So even with the strict controls of dimensions, we will have a quite different vibrational response of the finite guitar. So compensating the dispersion of parameter and targeting specific frequency during the build is, of course, the key to build superior instruments.
Okay, it's my turn now. So, basically, this all the research I've done in like musical acoustics and stringed instruments in particular, I was born from a very basic question that I posed myself when I started building mandolins, and it was: is there a right thickness for the soundboard, or is there a right thickness for the bracing? And so I think that every one of us has stepped into this question at some point. And one for sure can find very different answers. So you can Google it. So I reported some example. You can ask ChatGPT. You can look for plans, or you can measure like existing instruments and then try to replicate the same physical dimension. You can also make some consideration, which are sometimes empirical, on stiffness, mass. You can like make some trial and error, and you can base your decision based on your experience. But there are also some scientific methods which to me, who I am an engineer, were quite interesting from the beginning. Giuliano, can you please skip to the next slide? But here the point is, why should I use a particular method to design the soundboards, so the bracing and the top? Well, there are two answers to this question. One is to try to design instruments that have certain desired features. So you want a certain responsiveness, you want a certain timbre, you want to achieve a particular sustain. Well, there are many reasons in this regard, and it's not compulsory to use science to make such a thing. For sure, I think many of you have tried to develop their own instruments, but then I think that science can help you when things come to achieve a consistency in your building, in your design of instruments with respect to the wood properties variability. As Giuliano shown us before in a plot, well, both the density and the stiffness of the wood can really change a lot. These are all samples. If you look at the blue points about the Italian spruce, it's all spruce coming from the same place, which is the Val di Fiemme in Italy. All spruce from the same cellar. So basically, all trees that are cut in the very same region, which is a relatively small region, and so you can see that density can vary quite a lot. So from like 315, 320 to 400 and something kilogram per cube meter. And also the stiffness can vary a lot. And so for this reason, well, we can expect that if we build following the same geometry of the instrument, right, with the same thickness, for instance, we will have most probably like quite scattered result. Okay, here we are. So what is consistency in design? Well, first of all, it's like placing the resonances of your instrument precisely. This would avoid to have wolf notes, for instance. But not only, also it might be to achieve a reliable structural behavior. So avoid top from warping or breaking during time. And the third point was to achieve a target consistent loudness, which is mostly related to the monopole mobility. That is why we wanted to take into consideration the existing methods that can be used to design soundboards and compare them reliably.
So, for the study, we decided to use a finite element analysis. Why? Because in fact, there were a lot of calculation to be done, a lot of comparison to be made, and this method is really very powerful, exactly in this, to make comparison in between systems, or at least simple systems. So for this analysis, the first step is an original instrument that we know, and we replicate the design of this original instrument, that in this case is it's a Torres design of a soundboard, of a classical guitar. And this design is translated into a 3D drawing that comprises all the most important elements with a very close replication of dimensions and shapes. So we have the soundboard, we have the bracing system, we have the bridge. And we will see also later for each of these parts, we use properties that are assigned that replicates the properties of the actual materials. And then step 3, it's a finite element simulation. Finite element means, in fact, that we make a mesh. A mesh is in fact nodes and elements that recreates the geometry, and we assign for each one of these elements the characteristic of the materials, and this allows us to in fact study the behavior of this model with different conditions. So these are in fact the conditions of the study. We have around the soundboard fixed constraints at the edges. So this is simulating, in fact, an infinitely solid buffer where the soundboard is installed. We don't have for this study a complete box of the guitar, so there is no coupling with air and other parts of the box, because in fact we wanted to simplify the model and look for the trends. So look for the differences between different design and choices of design. We have also an homogeneous thickness of the soundboard. Very often in classical guitars, the thickness of the soundboard is not constant. It's not homogeneous all over the soundboard. Very often it is thicker on the center and thinner close to the edges. But in this case, we decided to use an homogeneous thickness, again, in order to simplify the study. And we have a thumb bracing with just a rectangular cross section. So we don't have a shaping of the braces. The braces are very simplified, but this also was a compromise that we decided to accept in order to have to simplify the simulation. Also because all of these parameters are parametric. So we will see later what it means.
Okay, so in this analysis, basically we are not dealing with real instruments, as Giuliano said, but we are simulating instruments. And I think that it's interesting to say that the power of making simulation is that you don't need to build actual instruments, but you can simply simulate them. And in particular, we have made many simulations, and this is because when you create this geometry and then put it into the computer, you can assign to the geometry particular properties. So the property of a piece of wood, a particular piece of wood that you want. In this case, we have assigned this geometry one at a time, 29 different sets of properties. These were related to actual measurements that we have done. So basically, we had 29 sets of red spruce. We have characterized it mechanically, and from the stiffness and the density were characterized. And then we performed one simulation for each one of these properties. So it's like simulating 29 guitars with the same geometry, for instance, or maybe it can be changed, we'll see later, but with 29 different woods. This is something that experimentally, also, I mean, it would be a nightmare for every luthier to do so. But with computer simulation, it requires much less time. So it's here is why it's we choose to use this method. Okay, so here we can see, for instance, in this table, we had the wood set number 1 to 29, and for each wood set, we can see the density, the longitudinal stiffness along the grain, the longitudinal stiffness across the grain, and the torsional stiffness. And in the end, we can see the sound radiation coefficient, or a number that somebody calls radiation ratio, which is, it's supposed to be an indication of how the wood is good to radiate sound. And we see that there are quite large variations. So in the last rows, you can see the minimum and maximum values. So the density changes quite a lot. So from 314 to 428. So it's quite a large variation. Also, the stiffness varies quite a lot. So from 7.6 to longitudinal stiffness along the grain, 7.6 to 12.4 gigapascal. And also the other properties vary quite a lot. But I think this is something most of us have experienced, like dealing with different pieces of wood, even if the same, even in the same species. Okay. So finite element analysis is very interesting because it allows us to make this simulation and evaluate different things. So in the center, you can see that it allows us to see the modes of vibration, which is something that on a real instrument would need to measure a spectrum and make some cloudy patterns. And here instead is very simple and easy. I mean, you run the simulation, which takes some time on the computer, a few minutes, but in the end, you can see very well all the different modes of vibration. Then you can like simulate the string pull. You can see on the left and see the rotation of the saddle as a consequence of the string pull, which is something you can measure on a proper instrument. But if you simulate it, it's very easy to measure. The image that you see here is out of scale. The scaling is exaggerated to see what happens. Usually, the rotation is much less. Another thing you can measure is like the soundboard stiffness, which is the same thing that you measure when you're trying to measure the monopole mobility. So you apply a weight on the bridge, and you measure the displacement. And the same can be done during these simulations. The other interesting things in this simulation, as Giuliano has told you before, is that we parameterize the thickness of the plate and the thickness of the bracing. This meant that we could change it very easily according to the particular design method that we are dealing with.
Yeah, just one thing that I wanted to add is that the finite element analysis, it's a powerful method. It's very used in a lot of industries because it is powerful, but it is very tricky. One of the key factor in this approach, in this methods, is to double check that the input data are fitting an actual real model. And this is something that we spend a lot of time at the beginning, in fact, of the simulation. In fact, these models come from other studies that have been done before, both mine's and Martino's. And this is what really makes the results very accurate and reliable. Because before beginning the analysis, we made a copy of an actual real soundboard, and we check with real measurement and the simulation that input and output are identical in the real sample and in the virtual one. Well, this is really the basis of this type of approach. And once you see that both the geometry and the conditions of the model and the parameters of the materials, in this case stone wood, are fitting correctly the model, then you see that the results are also very solid and reliable. So this is very important because, very often this type of analysis, I see that people are skeptical because, you know, it's very simplified. Of course it is. But what we are looking here are trends and variations and comparison between similar approaches. So the first design method that we simulated with the system is the traditional one. It's the simplest one. You just follow the plans. The geometry is fixed. It's the same as the original instrument. There are no info required about the properties of wood, and this is actually what factories usually do. So you know that these are the dimensions. You have a pre-selection of incoming quality of the materials, but it is very often it's just, you know, aesthetical selection. So you just have to cope with this dispersion. So you know that this is the material that you are using, and there will be variability according to this. So we simulated the dispersion of the parameters really according to wood variability. And in fact, we will see later on, this is the method that brings the highest variability.
Okay, the second method that we analyzed was the vibrational stiffness, and some of you may be familiar with this. It's a method proposed by Trevor Gore. This method assumes that the soundboard is a rectangular of constant thickness, and it's based on this really old paper. It's from 1949 from Mr. Harmon. In his work, Harmon tried to relate the frequency of vibration of rectangular panels of wood and plywood to the mechanical properties and the density of these panels. He provided an equation that can be inverted, and it's the one that you can see here, that gives you the thickness of the panel. It's the design thickness, basically, that you have to use if you want this panel to vibrate at a certain frequency. This frequency then was named by Trevor vibrational stiffness. And you can see that in the formula, this formula comprises the EL, which is the longitudinal stiffness of the wood, ER, the radial stiffness, transversal stiffness of the wood, and there's also GLC. I've written, but it's wrong. It's GLR, which is the torsional stiffness of the wood plate, and also there is the density. So basically, we shown you that we have considered 29 samples of wood. So for each one of these samples, we have calculated the thickness of the board according to the properties. So we put these numbers into the equation, and so for each of the 29 simulation, there was a slightly different thickness. So this took into account the wood variability to a certain extent.
So the third method, much simpler one, it's what we call the target mass method. In fact, we know that density is variable of the wood. Using the same thickness will therefore bring different mass of the soundboard. And the idea here is just to tune the thickness to always have the same mass. It's a very simple calculation that can be performed with a very simple measurement of the wood, and gives a target thickness. And so we simulated the dispersion of the parameter, just adapting the soundboard thickness to target a specific mass. A very simple method.
Okay, so fourth method is a bit more involved, but basically it's based on some real assumptions. So if you look carefully, and it's quite easy to do, to a soundboard, you can see that the board, the plate itself, provides mainly mass and little stiffness. So more or less 80% of the mass, while the 20% is given by bracing, and the stiffness of the soundboard itself without bracing is around 20% of the total stiffness. This is why we can design the thickness of the mass as for what Giuliano said before, using a target mass. So basically, we can choose the thickness so that the mass of the plate is always the same. We can calculate the thickness in advance, but we can also put very simply, if you want to do it in your workshop, you can just put the board in your sander and then remove thickness unless you achieve a certain mass. And then what about the bracing? Bracing mainly provides stiffness and little mass. So basically, we have designed bracing in each case to achieve a target flexural stiffness. What is the flexural stiffness? Basically, it says how much the soundboard is rigid. Basically, this is related to, you can see here, the flexural stiffness is the product of EL, which is the elastic modulus, the stiffness of the wood along the longitudinal direction, and I is the second moment of inertia of a section of the board. So it's not very complex, but too wordy to describe here. But basically, you can think that the stiffness of the board is determined by how the material is rigid, so longitudinal elastic modulus, and how thick you make the braces, and how thick is the soundboard. So this is a property of the geometry, and it's comprised into this I, which is the second moment of inertia. There's a way to calculate it. It's well, not very tricky. You can do it easily with an Excel sheet. So basically, we have use these two ways to determine the thickness of the plate and the thickness of the bracing.
Okay, there is a fifth method that we introduced also in this analysis that we call the brace tuning. So this is an hybrid method. So in fact, we consider that most of the mass is brought by the soundboard on the system, while the soundboard itself has a little lower part of stiffness, which is provided mainly by the bracing system. So we target the mass of the soundboard with the target mass method that we already seen, which still is very simple. And then we carve the thickness of the bracing from an overbuilt pattern. So we leave just a higher bracing system, and we with the parametric design of the model in the finite element modeling, we adapted the height of the bracing system in order to target a monopole frequency. Specifically, we targeted specifically the frequency of the main monopole of the soundboard. So we simulated the dispersion of the parameters with this hybrid method, which is very often used by builders. For example, it is the system that I personally use when I build my instruments. And this was the last. In fact, in the paper there is another one, but for sake of simplicity, we decided to just simplify for this presentation, right, Martino?
Yeah, 5 were enough, but there's a sixth one. So if you go to the next slide.
There is
yeah.
This one.
There's a last one, and so sometimes when talking to luthiers, we heard them speaking about like free plate tuning. So basically, they build the plate, they glue the bracing on, and then they make some measurements to like either by ear or with a microphone. They try to listen to the tap tone of the soundboard and carve the bracing until they find like a target tone that they want to achieve. We did the same with these simulations, but at least for this geometry of a classical guitar, this free plate tuning doesn't work actually. So we try to like carve the bracing to achieve a certain frequency of this of the mode that you see here. You see that is a mode is basically a bar mode of the soundboard, longitudinal bar mode with free edges. So it's simulating really like a tap tone. You can hold the board and then tap it on the side. But actually, it was very hard to like achieve a certain frequency in this case, and while performing very large changes on the bracing. So this would imply very large changes in the closed box, but not in the free plate. So basically, it has no meaning to use such a design method. We know it's very used also in violin making, but all the actual evidence, scientific evidences says that well, probably is not the very best method to use because there's no scientific foundation for using it.
Yeah, in fact, in all of the other models, the edges are constrained. There is a fixed constraint at the edges. So in fact, this is simulating the behavior of the soundboard as glued to an infinite mass and stiffness system. Of course, in the actual box, it will be slightly different. The conditions will be slightly different, but we will have the same modes of vibration that we actually have in the finite box. While, the free edges is completely different, behaves differently. So we calculated the eigenmodes. Eigenmodes are the natural resonance frequency of the soundboard for, of course, the first mode and the modes up to the 20th. and we average the values over the 29 sets of wood properties for each of these analyses for the 6 design methods considered. So here we can see the shape of the modes. The shape of the mode is always very similar because, in fact, the properties are similar, of course. So frequencies are shifting quite a lot, of course, but the shape of the mode is always very similar. And we can see that the upper part of the guitar, as we already know, is mostly not active, especially at low frequencies, while it is activated sometimes with some specific mode at higher frequencies. But we are talking about multipoles, in fact. And here we are with the first results with a traditional method, vibrational stiffness method, place mass, simplified beam, and the brace tuning method. So we can see that the percentage of variation, the black column is the Soundboard Monopole, and the gray column is an average between the 2 and the up to the second and up to the 10th resonance mode, eigenfrequencies. So we can see that the traditional method, which doesn't take into account the dispersion of parameter, the dispersion is higher. The vibrational stiffness is the second, quite close to the target mass. Then there is a simplified beam and the brace tuning method, which is, of course, the zero dispersion on the frequency of the monopole. But this is because, in fact, we are targeting the frequency of the monopole in the brace tuning method. So we can see that the monopole frequency is really very low, while there is still some dispersion on the other modes of resonance, even if it is still the lowest of the set. And here we can see, in fact, the delta in frequency of the monopole with the 4 method, which is interesting because this is also giving us a value of frequency. We see that in the traditional method, we can have in between 25 and 30 hertz of a delta on due to the dispersion of the tone wood parameters. This data is reduced by the vibrational stiffness method, but not as much as we would imagine. The plate mass method is slightly higher than the vibrational stiffness, while the simplified beam and the brace tuning method, of course, are much lower, the lowest of the set.
Okay, so another nice thing was to evaluate the structural parameter of the guitar. So depending on how you design the plate and the bracing, you will have a larger or a smaller dispersion of the parameters. Which are these parameters? They are like the soundboard stiffness and the bridge rotation angle. So if you use the traditional methods with same geometry but no control on the wood parameters, on the wood properties, basically you can have a wide dispersion of soundboard stiffness and bridge rotation angle. This means that some guitars are stiffer, some are less stiff, and in some the bridge rotates a lot when you pull the string, and in some does not rotate as much. By using vibrational stiffness, this variability is reduced with similar result to the target mass. In the simplified beam and brace tuning method, well, there is even quite a bit a smaller variation, in particular for the soundboard stiffness. So on the left, you can see a plot. Here I plotted the soundboard stiffness measured as for the image above. So you put a weight at the center of the soundboard, and you see how much the soundboard deflects. And in the y-axis, I reported the bridge rotation. So how much the bridge rotate when you pull the string, when you first string the guitar and pull the string and you put it in tune. And so basically, these two parameters are related. This is another side result of our simulations, but it's quite interesting because you can relate the two things quite reliably.
We plotted also the variation of the monopole mobility, which in fact is quite similar to the one of the monopole frequency. If you see the behavior, with just a slight difference for the brace tuning, which of course in this case has a slight variation. This is an interesting data because in fact we can see that vibrational stiffness is quite good from this point of view as a method. Again, the traditional one is shows the higher dispersion. The plate mass, in fact, it's not the lowest one because of course the mobility is directly proportional to the mass, but also to the stiffness of the soundboard, inversely proportional to the stiffness. And the plate mass method is not controlling, in fact, the stiffness of the bracing system, which is taken into account in the simplified beam and the brace tuning method. And this is why these two are still, again, the most interesting of the group. The simplified beam.
Sorry, Giuliano. Just maybe somebody's not familiar with monopole mobility, but it's a measurement which is related to how an instrument is loud, how it's related to the loudness of the instrument. So a large variability means that if the properties of wood change, you will likely have some guitars that are very loud and some that are not very loud. While if the variability is little, so you can like replicate also the loudness of your instrument.
Oh.
Yeah. Okay. So in the end, we made an overview.
We are really pushing. We are really pushing, but we need to do like this because time is a tyrant. So
time is flying.
We are close to the end.
Yeah, almost. So basically, we wanted to compare these methods. So some methods are very complex, very involved. Some are very simple. So the traditional method is the easiest one because you don't need any knowledge about the wood properties. You require zero measurement of the wood properties. But it's also the one that gives the more scattered results. Vibrational stiffness is a bit better in terms of like scattering of the results, but it's very complex to implement. So you need to measure the density and the stiffness along the 3 different directions of your plates, which requires a bit of time and expertise. Plate mass is very interesting because it requires only the knowledge of the density. And it gives quite good results, and it's on average is comparable to the vibrational stiffness, but it requires only 1 measurement instead of 4.
That simple measurement, especially.
Yeah, 1 simple measurement. So just measuring the density or measuring directly the mass of the plate. So you can build it so that the mass is always the same. You can like drum sand it unless the mass is the correct one, without drum sanding too much, of course. The simplified beams requires 2 properties, which are the density and the longitudinal stiffness, which, well, can be measured and are not so complex to measure anyway. And the last method, which is the brace tuning, requires the measurement of the density alone, and then to measure the monopole frequency of the closed box. So you build the instrument and you let the bracing with a higher thickness with respect to the final one, and then you carve them slightly, little by little, taking measurements unless you achieve the desired monopole frequency. Well, so it's like 2 measurements overall.
So we decided to give some target values for all of this data because, of course, it is interesting, especially when you are beginning to have some references. For classical guitars and steel string guitars, of course, the traditional method is just, you just follow the plans. But for the vibrational stiffness, you have to have an idea. And for this, we have an Excel file that is very powerful and very simple to be used to calculate the vibrational stiffness from the parameters of the tone wood. So you need to know the main parameters, such as the stiffness of the longitudinal bending mode and the density of wood, but you can calculate with a simple Excel file the vibrational stiffness. The plate mass, of course, it is according to the dimensions of your instrument. 100 grams and 150 grams for classical string strings are a starting point that puts you in the ballpark. But of course, it can be optimized as long as you build. Of course, the thing here is to starting with a build to take note of all of these values and then to adapt the values as long as we proceed with the next builds. Then for the simplified beam, we give an idea of AE, which is flexural rigidity of the section of the guitar. I think that we have here, we can see here the AA section there. It's the part of the soundboard that we use to calculate the flexural rigidity of the soundboard, and that we are here exemplifying. You can see, of course, a steel string guitar has a much higher flexural rigidity than a classical guitar. In this case, 45, it's still a value for a very responsive guitar, because with the Martin type X-braced instrument, you can reach up to 100 Newton meter. So it can be much higher.
But also the one for the classical guitar is relatively
the Taurus one,
relatively low value. Usually is around 15. Sorry, I've put this number, which is the one we use to replicate the Taurus guitar, and this is good to replicate the Taurus. But just remember that this guitar is from 1800, so it had gut strings and so on. So the tension was lower at that time. So nowadays builders tend to build like a bit stiffer guitars.
Yeah, but it can be considered a good starting point. And for the brace tuning, the resonance frequency of the soundboard Monopole, usually it's around 180 to 195 for classical guitars, and in steel string guitars it can vary. 190, it's a bit higher. It could be from 170 to 200, 220. The thing is that steel string guitars have a very rich declination of models, so it can vary a bit, and you should have an idea of what you are targeting in your design.
Just a side thing is that on the previous table, the vibrational stiffness values are those like suggested by Trevor Gore. Yeah. Okay. Well, basically, the vibrational stiffness is the same value which was suggested by Trevor. We found the other values based on a bit on our experience and on the simulations also, the values about the other methods. Of course, as Giuliano pointed out, these values are indicative, and then you have to tune them to your specific design. And well, that's it basically. Okay, you can jump to the last slide if you want. So to draw some conclusions, well, we've seen that if you build guitars just following geometry, you will have scattered result. And well, I mean, that's okay if you want to build them traditionally, but just the thing is that you can expect to have different timbre, different responsiveness, and so on. If you want to implement one of these methods, well, if you measure the wood properties, it's interesting because I mean most people just measure the properties of the wood and then like use them to like select wood. But instead of selecting, at least what I do is like trying to do the best with the wood that I have. So I use these properties not just to select wood, but also to design the plate and the bracing. I saw a question by David Lang that asked if the plate mass was about the braces or the top only, and the plate mass is about the top only. So just to answer a short question. So first, we suggest to measure the properties, then to use them to design your plate, to perform then the measurements on the finished instrument. And as we can see, as we saw, basically in all the methods, except from the brace tuning, there is always a residual variability. So the thing is that if you really want to place resonances where you want, it's very important to like fine tune the instrument when it's built at the end. So find a way to do that. So we didn't suggest any particular method, so it's up to you to decide which one to use if you want to use any. The good news about this work was that the target mass method is the simplest one, but also brought excellent results, which are, I would say, more or less the same as for other with respect to other more complex methods. The best one, if you want the best control, is of course fine-tuning the monopole frequencies, but the monopole frequency by like changing the height of the bracing by scalloping them, starting from a like overbuild pattern. This implies a bit of complexity because you have to work on the bracing on a finished instrument, or at least on the plate mounted on the sides, working on the soundboard attached to the sides. But well, to us, it's quite worth doing it, and in fact, it's what we sometimes do. And well, yeah, I think that's
also because if you're not tuning a little bit the bracing system, I want to say that it is almost impossible to get your desired values just by, even also if you consider the properties of the materials. It's the coupling with the rest of the system, which is the sides and the back and the air volume and the tuning, the resonance frequency of the first mode shifts at least the main monopole by an extent that cannot be just calculated. So a little bit of tuning when the box is closed and the guitar is stringed and finished is, I want to say, necessary. So this means that if you really want to tune the Wolf notes at the best, you need to act on the bracing system once the instrument is finished.
Well, there is no, basically one of the interesting result is that there's not a perfect design method. So there are some that are better than others that can bring you to a reasonably good result, but then you have to fine tune your instrument in the end by making measurements, like with a spectrum analyzer, something which is not very complex, but you have to do that. Yes. And well, I think that our presentation is finished. So if you have any question, we will be glad.
Yeah, I just wanted to say that this work is also brought within the hub of acoustics. Unfortunately, we don't have Simone and Andrea with us today. We say hello, bye, and keep in mind that we are also offering with the hub of acoustics seminars, information. So yeah, we will have some news to talk about very soon. And yeah, I think that we can open to questions. So,
well, I think we can answer the questions that we had in the chat.
I can start working through those if you want. Let's see here. Okay, was any arch included in model? David, are you there? David Lang asked this question. Are you asking if an Archtop instrument, or am I misreading Arch? It sounds like yes.
I guess
Archtop instrument.
Please, Martino.
Okay. Well, no, we didn't consider any arching. This was a classical guitar, which is almost flat. Well, sometimes some of us build like slightly arched plates, but slightly arching just slightly affect vibration frequency, stiffness, and so on. So we didn't take that into account. No, so it is just for like classical guitars, of course. But since the let's say the physics is very similar to all the other instruments, like flat instruments, so we can say with confidence that the results are
because in the
reliable
book,
for steel string.
In the book, I also simulated the difference between a flat and a different arch of the soundboard, and this is affecting mainly the monopole, it is also intuitive because, of course, the monopole is the only resonance that affect the wall surface of the soundboard, and has a very little influence on the frequency of higher order mode. So no, we didn't take this into consideration, but the geometry is the same for all the models. And the boundary condition we already talked about is a fixed constraint.
Let's see here. Plate mass and braces and top or top only.
I think I've answered before, but anyway, just to say it again, with the plate mass or target mass method, we just measure the mass of the plate alone without the bracing. This is because the plate accounts for 80% of the mass of the top, while bracing accounts for 20%. And also bracing is always there. So if you vary the height of the bracing, you're varying of a small amount, something that accounts for a small amount of the total. So it's a second order variation to say so.
Cool. And then Paul, you want to pop on and ask your question?
Yeah, I was just wondering if you're able to correlate the measurements with the bridge glued on the bridge and without a bridge prior to gluing the bridge on, what the change in the monopole mobility is.
Mm-hmm. Yeah, definitely to remove and attach the bridge would change the monopole. We didn't perform any simulation for this in this regard. We didn't, at least we did them, but we didn't publish them. Probably this would be helpful, so you can like tune the bracing and the top before gluing the bridge. But yeah, the bridge is very important. So my personal suggestion would be to like attach the bridge and then fine tune the resonances. The resonances, if you want, because attaching the bridge, if the mass of the bridge changes only slightly, you will have a quite important effect. And also, if you change the geometry of the bridge or the properties of the bridge wood, you will have an influence on the vibration modes of the top and on the stiffness. So this is why we didn't take into account like bridge on and bridge off. It was also to make like the article a bit simpler, because we have performed like 29 simulations times 6 design methods, which accounts for like almost 200 simulations, and it was really hard to explain all of them. So we didn't want to introduce a further complexity. This is also being studied. Anyway, there's an article from I think a Spanish guy. We cited it through the article. It's called Eleja Barrieta, and he simulated the effect of the bridge on the resonant frequency, I guess, on the resonant frequency of the plate. So you can refer to that article if you were interested.
And keep in mind also that different bridges geometry and materials affect differently the frequency, because of course the bridge at the same time adds stiffness and mass, and if you think these two change could balance themselves. So eventually, it is the higher mass that really drops the resonance frequency of the monopole from before and after, but also its rigidity is pushing higher. So especially the cross mode as the cross dipole and the cross tripoles frequencies that are shifted much higher. So different bridges design also change the way the bridge affects this resonant frequency, and so this is why also we didn't consider it in the study. What we studied is the traditional design of the Torres guitar. So about the Garrone's method here, I don't know this method. Martino, do you know? Garrone makes a mock-up of a guitar body and clamps the top to it to facilitate tuning.
Yeah. Garrone is an Italian luthier who's been working with Cuzzocoli, which is an Italian engineer. They made a book about designing guitars and so on. I think the method that they use is quite it's quite old with respect to the ones that we use nowadays, like with spectrum analyzers and so on. But it's because when they did their work, such modern method did not exist. Anyway, yes, they do a mock-up of the guitar, and it's something you can do actually, like to clamp the plate on, like, let's say a fake a mock-up size to try to tune the frequency. Of course, you can do it, and it might be useful if you are working consistently. So if you replicate the geometry of the guitar all the time, and it's always the same. So I would say yes, why not? You can use this method as well. But if you're changing between like guitar models to make a mock-up for each model, would be quite time-consuming. And so, well, in my opinion, the best option would be to tune the bracing to achieve the frequencies that you want, for instance. But well, there are many methods, so you can choose to follow the one that suits you better.
I am adding here that if you want to clamp the soundboard to a support, it is very, very important if you use a radius to replicate the radius on the edges of the support, and to pay attention to the clamping system, because it can vary. It can vary quite a lot. If you use a radius on the soundboard, actually the soundboard will be radiused, and when you clamp it to a flat edge, you will add a stress in the material. And also when you clamp, it's very delicate. I can say that I try to build a support to clamp the soundboard in order to perform a tuning before gluing it to the sides. But eventually, I modified my process, and now I tune the bracing once the soundboard is glued to the side, and the sides are in the mold, because it is adding a lot of precision to the process. But yeah, I would say that it is perfectly doable, but you need to design a jig and a fixture that really works very well, and that gives you repeatable results. So I think, can the top be clamped closed? Yeah, it's a similar question.
Sorry,
Yeah.
Giuliano, I have uploaded I have shared in the chat the name of the title of that article that dealt with the well, it's named "Influence of the Bridge on the Variations of the Top Plate of a Classical Guitar." So now you have the reference, just in case you want to have a look at this particular work.
Thank you, Martino. So Jose Luis is asking a similar thing about can the top be clamped closed to get a ballpark mountable frequency to easily curve the braces? Yeah, it's the same thing. I mean, if you want to clamp the top on the body, again, pay attention to how you're doing this, because it's just mechanical. The way you are coupling the soundboard with the support, and the way you are constraining the edges of the soundboard is really affecting its vibrational behavior. So you just have to design a method that it is repeatable, and pay attention to the doming on the sides. So Craig is asking about different bracing styles, different bracing and falcates. So this is fun bracing. The falcate bracing is, of course, the bracing designed by Trevor Gore in his instruments. I would like to think that falcate bracing can be considered quite similar to a fan bracing. It is symmetrical, and it is the bracing is really we have two main braces on the longitudinal axis.
Four main braces. Two long ones.
Two main braces on the longitudinal axis, and then four. The external one are going on the cross direction. I mean, of course, it's a different bracing style, so we would need to perform the same simulation to check the dispersion with falcate bracing. But I think that we can we can relate the results also to different style of bracing, because in fact we are considering two elements that are the soundboard, which is really bringing the radiation surface and the mass, most of the mass of the resonance system of the monopole, and the bracing system, which is bringing in most of the stiffness and a little part of the mass. So if we consider separately these two elements of the system, I think that we can relate the results with different designs. What do you think, Martino?
Yeah, definitely. The point is that one could simulate all the possible types of guitars, but this would take a lot of time. But still, this simulation, like, want to highlight the main aspects. So mass is in the top, basically, and stiffness is in the bracing. And although different type of bracing would result into different timbre of the instruments, of course, they would result in a different mode ordering and a different mode frequencies. Well, the trends, we expect the trends to be really similar. So if you shave the bracing, the frequency will get lower for any type of bracing. If you make them higher, they will be stiffer anyway. So I would say that the trends and also the variability that we observe, it's arguably the same, independent of the bracing type. Yeah.
So Paul is asking, why not glue the top on first? Yeah, that's a very good idea, and this is what I'm doing, as I tell you. It depends on on how you design your process, your build process. Yeah, I think it's the best way to do this, and this is how I'm doing it. Is there any software usable by luthiers to do what-if scenarios using FAIR? For example, what happens if I add the boucher bar? And Paul is asking similar. Yeah, it's a similar question. We use the finite element analysis to design new instruments, and this is something that normal people can use. I mean, yeah, normal people. I don't know what it is. Normal people. I think.
Yeah, Paula, I need to get.
Yeah.
Paul, are you under the impression that you're normal? Oh, okay. Clarification, smart.
Well, the question is, do you know any normal luthier?
Yeah, this is a good question.
Me included, huh? So if you get yourself so much in trouble building instruments, you're probably not average people, let's to say so.
Martino, I begin, then I let you. My point of view about the use of finite element modeling to design instruments. The most difficult part is not a technical one. I mean, you have the data, you know the parameter of tone wood. You can find them almost everywhere. And with the fact that CNC machine are becoming much more common use today, means that people are also learning how to design in 3D, which is required for, of course, finite element analysis. So it's not the technical thing. It is mostly the method that you have to learn. How to fit a model to something that is already existing, and how to simplify the model, because it is important to reach the simplest as possible model to get the data that you're looking for. It's really about method and being able to validate the results. And this takes quite a long time and a bit of experience. So I think everything is feasible, of course, but you have to dedicate. I mean, if you are working building instruments, most probably you will not have a lot of time to dedicate to this. So, but again, it depends on, how strong is your will, I guess.
Yeah, I think that. Sorry, Paul, if you want to go ahead. No. Well, so in my opinion, the point is that. Sorry, window opened in front of the chat. You can use finite element modeling. It's very useful, but it's also very complex to use. with complex, I don't mean that it's difficult to run. So there are programs that allow you to import a geometry and run your simulations. But the point is that you need to define a lot of parameters for the materials. So for the wood, you need to define all the elastic constants, the density for the different woods you have. So I would say it's good to make simulations if you want to know what's going on up to a certain extent. But personally, to like design the plates, once I have understood the basic principles like modes, most frequency, which kind of mode I can observe, etc., then I prefer to relate to simpler models as the ones that we have shown today in this talk, because in these models you can have a much smaller number of parameters. So basically, the behavior of well, to say in a different way, by finite element modeling, you can understand that the behavior of the guitar is linked to geometry and two main properties of the wood, which are density and stiffness along the grain. So once you have understood these, then it's no more necessary to use finite element modeling. And indeed, to design my instrument at this point, I don't use it, but I just use simple spreadsheets that allow me to make simple calculations and very easy and quick calculations. Yeah.
Martino,
Yeah.
just a question to clarify what you just said. You said mass and stiffness along the grain. So somewhat discounting cross grain and twisting grain stiffness then for your calculations, is that correct?
Sorry, I didn't understand a part of the question.
You mentioned stiffness and mass, stiffness along the grain and mass as being your two really important characteristics. And I'm just asking, does that mean you're discounting to some degree cross grain stiffness and twisting stiffness?
Yeah, well, in the simulation, we have taken into account also the variability of the cross-grain stiffness and of the twisting stiffness of the plates. In particular, if you look into there's a plot at the end of the article that takes into account a large variation of the cross-grain stiffness and its effect on the mode frequencies. But what we saw was that the cross-grain stiffness has a little influence on the behavior of the guitar, both on the modes of resonant modes and their frequencies, and on the structural features of the stiffness of the guitar and so on. This is something that is quite well known in the field of guitars by scientists. And also Trevor in his book takes this into account, and he says a very wise thing is that if you really are looking for a very stiff soundboard across the width, so instead of choosing a very stiff wood, you can put a brace there, and which accounts for that stiffness much more than choosing a wood with a large stiffness. So I don't know if this makes sense to you, but
yeah, thank you.
Okay, so David's asked, what is the relative importance of radiation coefficient and hue to use the use of simplified methods? David, you mean radiation coefficient and Q? So the Q factor was not considered during the study. The Q factor is in fact affecting the amplitude of a resonance exactly at its resonance frequency, and of course the decay, but it was not considered for the study. Radiation coefficient, the radiation coefficient is in fact proportional to the stiffness, and so mass divided by stiffness at cube squared. So it's a data that in fact tells you about the capacity of a piece of material, of a piece of wood, to transfer energy, mechanical energy, into acoustic energy. And in fact, it is not directly related to the study that we show today. that was mostly centered in the analysis of the frequencies of the main resonance mode and the higher modes.
Well, actually, there is a part about this in the article. We have not shown it today about the
Yeah, it's not here.
maybe I don't know, Giuliano, if you can share a screenshot of the article. I have no. I can't share it.
I mean, all else equal, when using this method, you can also, David, you can use the microphone if you want. We can directly talk. Okay. So target
David,
mass.
are you having a hard time unmuting? I could ask you to unmute and it'll probably pop up.
Okay, can you hear me?
Yeah.
David Lang. Yeah, no, I'm just curious, when you have this tremendous amount of data that we can now collect on an individual piece of wood, and some of them are material properties like radiation coefficient. And I'm just wondering, if we use a simplified method such as target mass, or Trevor's methods of target thickness, does the radiation where would you put if say you have several boards, all have roughly the same target mass, how much emphasis would you place on the Q of that board or the radiation coefficient of that board when selecting between three different boards, say, where all else is equal? There's people out there now that are marketing wood based on radiation coefficient and Q, and I'm just wondering, are those truly important factors that need to be taken into account when building let's say, a high performance classical guitar?
Martino, I begin and then I let you reply. Okay, from my point of view, the Q factor it's always important, and it is because the Q factor tells you, it's really the quality factor. It tells you about how a specific piece of material is resonating, how it is in fact dissipating energy to produce sound or to produce heat. And in my point of view, it has to be high, also because it's important not only at the main resonance of the monopole, but also at higher frequencies, of course, where you have harder modes such as the dipoles and the tripoles or the multipoles. And I think it is important, but today we don't have a study on this matter that is really showing with an analytical study the importance of this data. Can you please, Diane, silence again?
Yes, I understand that the purpose of your study didn't include these things, but as we're out in the field trying to design instruments, it's interesting to contemplate which is relatively the most important. For example, if you have a guitar built with high Q wood and a guitar built with low Q wood, can you actually hear that difference on that instrument? I've never had an opportunity to do that, although I do measure all of these things. I have tried to aim to use high Q wood as often as I can, or as much as when I have it available. I'm not sure I can hear the difference.
I mean, the only study that exists today about this has been done by Taylor Guitar with Pacific Rim Tone Woods. They built 3 different instruments with low, medium, and high Q, and according to their results and the people that played the instruments, there is a difference. And I want to say, of course, there is a difference. I am not surprised. The thing is that you start from a simple piece of wood that has a Q factor. For the spruce, for example, an average Q factor can be 150, and you eventually finish with a Q factor of a soundboard of the resonance of the monopole around 40, maybe 30, 40.
I see.
So all of the other parts are reducing in a very strong way the Q factor of that resonance, and this you can measure very easily with the TP software, with my software, where you can check the Q factor of each resonance of the instrument. So it goes down a lot, but still I am talking about the monopole. So there is the spectral distribution of all the other resonances is of course important, and sometimes today it is difficult to tell you exactly what is the importance of this specific parameter over the sound of the instrument. At least there is no actual study that is focused on this analysis.
Okay, thank you very much.
No, you're welcome. And for the radiation coefficient, Martino, I leave you to the radiation coefficient.
Yeah, sure. So first, we just to say a last point, we didn't consider the Q in this study because we didn't want to add further complexity. About the radiation coefficient, yes, we took that into account. There was no time today to explain it thoroughly. Anyway, if you have a look at the article, we also reported this thing. So basically, in principle, one should think that using high sound radiation coefficient would result in a guitar with a high sound throughput, with a large loudness. And since we can measure loudness by the monopole mobility, indeed we measured it in our simulations, and we tried to find a correlation between the sound radiation coefficient of the instrument and the monopole mobility. There are some trends. I think I can show them, but I have no. I cannot modify the. I cannot share my screen. I don't know if I can, or if Giuliano can share the images of the articles.
Try to.
Oh, okay. Yeah, I can. So let's see. Okay, can you see this?
Yes.
Okay, so I'll zoom in. Sorry, there's plenty of data. This is all the data of all our simulations, so it's really a lot. So it's a bunch of data for each simulation. Well, but we'll focus just on one simple thing. So let's see this plot on the left top. So on the x-axis, we have the sound radiation coefficient, and on the y-axis, we have the monopole mobility. So this is for the traditional method, so same geometry every time. And this tells us that these are 29 points, one for each set of wood. And this tells us that, okay, well, if we choose a high sound radiation coefficient, we maybe have a large monopole mobility, but it's not always the case. So say you pick up 15 as a sound radiation coefficient, so you can have instruments with like 26 second over kilogram monopole mobility, or instrument with 23, which is a quite large difference. So if you use this design method, the sound radiation coefficient has only a marginal importance. If you pick up other and the overall variation is very large, so it goes from 23 to 28. So you may have some instruments that are very loud and some that are not very loud. While if you adopt other design methods, so here is like vibrational stiffness here on the right. Then we have simplified beam and brace tuning. If you adopt these methods which are different, you have different results. So in general, well, here is the plate mass, and the one on the most on the right. I'll just plot these now because it was not here. So it took a bit of time. That's why I was distracted, but I was listening to you anyway. So here you have the sound radiation coefficients versus the monopole mobility for the plate mass design. And the interesting thing is that with the plate mass, the variations are very low. So you can go from 24 to 26, which is a 2/20, 10% variation, for a very wide span in sound radiation coefficients. This means that rather than choosing the wood that has the largest sound radiation coefficient, you can choose the nicest piece of wood that you have, and you will have similar results even using this method, for instance.
This is because in this method on target mass, we are compensating, in fact, the density. The density is a cube in the radiation, the sound radiation coefficient data. So it is very important. And with the target mass, we are compensating the differences in density of wood because we are thicknessing the soundboard according to a specific target mass. It means also that the final soundboard will have a different thickness according to the sound radiation coefficient also. But we considered this on the study, right, Martino? And in fact, we have also a variation coefficient of the thickness with different methods that we didn't report here. Do you have it? Do you have it here, Martino? If I'm not wrong, we moved from 1.9 to 2.4 millimeter of thickness.
Yeah. Okay. Here we are. It's this table that tells us for the different design methods the variation in the thickness of the soundboard. So on average, it's 2 millimeters, and the largest variations are from 1.7 to 2.4.
Yeah.
Which you might consider very large, but in the end, it's what allows you to have always the same mass. Well, it's well within like reasonable working tolerances.
So in this case, choosing for selecting the sound radiation coefficient will help you to reduce this difference, of course, and to build with, because you know, with 1.7 millimeter of thickness, you can start to be sensitive to print through of the bracing to the soundboard. So if you can select a bit your wood, everything goes smoother. So I mean, from our point of view, everything is important. A small selection of wood, it's always important, and knowing what you are buying is helping to reduce bad surprises. Also because, and just to finish, when you have a very good Q and you have a nice sound radiation coefficient, it means that also that the board that you are buying is sane. I mean that there is no run out, that the fibers are correctly moving all over the board. So yeah, from my point of view, it always makes sense.
1.7 then would be a particularly stiff piece of wood, yeah?
Sorry, it's the thickness of the soundboard.
I'm saying, but the wood that you started with to end up at 1.7 would necessarily be a really stiff piece of wood, or not necessarily? I'm just saying is that the stiffness becomes a negative in that situation because your board becomes impractically thin.
I mean, in this study, we compensate the stiffness of the soundboard with the height of the bracing system, keeping in mind that there is also always a relation in between density and stiffness of tone wood. So usually, yeah.
Here I think that the point is 1.7 millimeter were the densest woods. So the denser is the wood, the thinner the plate should be. So this thickness is dictated only by the density. And then we can play with bracing to recover the right stiffness. So stiffness is mainly in the bracing. It's 80% in the bracing. So just a little variation of the bracing would compensate for having a board that is very thin. This is the idea.
Can I just have one question that's kind of related, not straight to the paper, but can you just qualify what you can and can't test for when the top is glued to the sides, but there's no back on the guitar? Can you get an accurate monopole mobility in that situation?
So Okay, so you're saying you glue the top on the sides without the back.
Yeah.
Okay, and if this can be useful?
Yeah, what can you measure? I know that you can measure some things, but not others. Obviously, you can't get the back frequencies, but can you measure the monopole ability? In my situation, I have the structured side, so I don't need to put them in a plant. I don't need to put them in the mold.
Yeah. Okay. It's something I don't do because building mandolins, especially ball back mandolins, you have to really attach the soundboard to the ball back, and there's no such thing as a back, so it's not possible. And on the bluegrass and mandolins that I build, I usually glue the back on before and tune the back and then put the top on. So for my construction method, I have no data to tell you. But yes, in principle, you can tune the bracing while you have attached the top on your sides without the back. Definitely, the thing you have to fill up the gap because unless you close the instrument, you don't know what's happening when you couple back top and the area side. So you have to build that up with experience, but in principle, yes, it's doable, definitely. Well, I don't know if Giuliano has any consideration in this regard.
Yeah, I usually do this type of measurement because it allows me to, when you measure the parameter of the monopole before and after gluing the bridge, you can really understand and measure, in fact, how much mass and how much stiffness the bridge is bringing to the system. So it is very helpful to understand how to improve the design of your bridges. And of course, you can measure the monopole mobility before putting the back. You will measure only the resonance frequency of the soundboard without any type of coupling with the rest of the box, but it's very useful to understand how the soundboard and the bracing system works by themselves without coupling. So yeah, from my point of view, it's very interesting. But I suggest you to take care, because even if you have structured sides, if you don't fix, if you don't strongly attach the sides to the mold, the sides will always vibrate because they have a free end. So the fact that they are stiff because they are structured is just shifting the resonance frequency higher, but the resonance will always be there. So I suggest to always use the mold when you perform acoustic measurements. For the monopole mobility, when you measure the flexion of the soundboard, maybe it will not be a big difference. But for if to measure the resonance frequency of the monopole of the soundboard, I think it's better to use a mold.
What if you clamp the back on instead of using the mold? Glue the top on, clamp the back on without gluing it. Would that be the equivalent of the mold, do you think, or not as much?
No, yeah, of course it is feasible, but as I said before, take care about the fixture, the jig that you use, because you have to be able to make one measurement, remove the top, put it back, and have the exact same result. So this is important.
Thank you.
You're welcome. So, as a general consideration for everyone that is interested in having more details about this paper, of course you can send us a message to me or Martino, and we will give you information. Are there other questions?
Yes, Flora, and do you hear me, Giuliano?
Yeah.
Yeah, just a small question you missed on the chat, which is, did you use a reference bridge in your finite element analysis or no bridge?
Yes, there was a bridge.
And how which mass did you choose for the statistics? Because you would have to have the same mass for every simulation, of course.
Yeah, it was the same mass for every simulation. I don't have the real number here, but it was like we copied the geometry of the Torres guitar and we used like an average
Rosewood,
value,
right?
for the Rosewood bridge. So I don't know the real number, but reasonably
should
would
be
be
around
like
18 grams, something like this.
yeah, something like that,
Okay,
like 15 or so. Yeah,
Okay.
Yeah,
cool.
maybe 18. Yeah.
yeah,
Okay,
maybe
cool.
18. Yeah.
Okay, super. Thank you.
You're welcome.
I think there's a last question that I see in the chat, and it's by Jose Luis Ochoa. The focus of the article is the top, yes. And can the concepts of the article be applied to the back also?
Right, it's a very interesting question. Of course, keeping in mind that the back in this case should be active, because if the back is passive, so it has little contribution.
But well, I would say yes, indeed. Like Trevor gives like values of the vibrational stiffness also for the back plate that can be used for when, as Giuliano said, when you are designing an active back. So if the back is active, yeah, you have to find a suitable method to design it. And actually, you can apply the same method. So like the target mass would be okay. In my Archtop mandolin, I use exactly that method. No, not properly. Sorry. Well, anyway, I tuned the bracing to have the right frequency of the back on my mandolins. That's why I attached them to the sides before the soundboard. But well, this is a whole another story. And yes, indeed, you can use them. Yeah, sure.
Keeping in mind that it will affect differently the sound of the instrument. Of course, the soundboard is the most sensitive part of the guitar, while the back, if active, can add one or maybe more resonances to the sound, but mostly one. And it would change a little bit also the dynamic character of the sound of the instrument. So yeah, it is very important to consider the mobility of the back when designing an active back. But yes, it's the overall design of the instrument then.
Yeah, thank you for your question, because it's really interesting.
Yes, it is.
Can I go off topic a little bit and ask you about those tops that you have hanging in the back there with the triangular shape on the top?
Yeah, they're mandolin soundboards. They're not cut to the right shape yet. So here maybe you can see the outline. They're not. They are not. Sorry, ritagliate, come si dice, Giuliano. They're not trimmed yet. Yeah. So they're triangular because it's easier to handle and work on, but just that reason.
I love it.
And these are designed with the plate mass. So there are like 5 here on my back, and each one has a slightly different thickness to have the same mass for each one. Yeah, that's the idea.
Giuliano, do you think you get Martino to come back on and? Oh, go ahead, Max.
I'm just saying that you can choose to make balalaikas as well with the triangular.
Yeah, sure. They're universal soundboards.
I don't think making a functional balalaika would be keeping within the spirit of balalaikas overall. But Giuliano, do you think you can get Martino to come back for an interview about what he's building, what he's getting up to in a shop?
Of course. That in fact, Grace already proposed this, and of course with pleasure. And I think that I will leave up to some other contributor of the Lute group to interview Martino. So
we can certainly talk about that. Yeah, I'd be happy to do it, but probably maybe Max would be a better choice. Max.
Oh, nice. Well, I'll be glad to talk about mandolins if anybody's interested. Yeah.
Okay,
sure.
So now we can do it in Italian. Great.
Yeah. I've said for a while, like, it does not have to be an English centric operation here. So if it happens to be in Italian, that's fine. We'll just need Spencer to translate for us. Anyway, you want to put a pin in it here and And
Yeah, of course. Robert, as I said, send us a message, okay?
yeah,
To have more info. Anyone who's interested.
can everybody unmute and thank these two fellows for taking time
Great
to
stuff,
hang out
guys.
with us? Thank you very much. It's very nice.
Thank you very much.
Thank you.
Thanks a lot.
Guys, it was awesome.
Thank you.
Thank you, everyone, and see you the next one.